Welcome back, everyone. In this video, we're going to look at another example of using trigonometric substitution. In this example, we're asked to find the area enclosed by x squared plus y squared equals r squared. That is the just general area of a circle of radius r centered at the origin. And well, our first example was a slightly easier version of this problem. We were looking for the area of that circle of radius 1 in our first quadrant, and we knew that that was pi over 4. We also know the full area of our circle is given by pi r squared, but now we're actually going to derive that formula from scratch using calculus. And the way we're going to do this is really similar to what we did in our last example. Things are just going to be slightly changed a bit because now our radius is a general radius r instead of the unit circle with a radius of 1. So the first thing we might want to do is express this area as a definite integral. And so we're going to try to set up this definite integral to look similar to the one we saw in our previous example. So maybe we're going to focus on that piece of our circle in the first quadrant. That's going to be 1/4 of our circle. And then, well, if we multiply that by 4, we'll get the area of our entire circle. All right, so now we're going to need an equation that describes our curve for the top of our region. And we can get that equation by solving for y in this general equation for our circle. So if we solve x squared plus y squared equals r squared for y, we get y is equal to plus or minus the square root of r squared minus x squared. And if we just want that top half piece, we'll take the positive square root. So we're going to integrate the positive square root of r squared minus x squared. We're integrating with respect to x, at least for now. And the interval of x values that we're going to have to go through is going to be from 0 to r if we want to get that first corner piece in the first quadrant. So our x values go from 0 to r. But like we mentioned, that's only going to give us a quarter of our circle, but we want the entire area. So we're going to have to multiply this whole thing by 4 to pick up the entire area of our circle. And remember, we're trying to now get this right-hand side of our identity to resemble our integrand function, the square root of r squared minus x squared. Remember, in the last example, we were able to make a substitution for our variable x, and that's what we're going to be able to do here. We cannot make a substitution for r because r is our constant representing the radius of our circle. And well, we might see that we're running into a problem already because our manipulated version of our Pythagorean identity is not r squared minus sine squared, it's 1 minus sine squared. We really do need a r squared to show up there. So the way we can make that happen is just by further manipulating our identity. We're going to introduce that factor of r squared to both sides of this equation so it remains true. And it's going to be now more helpful for us. So if we multiply everything in our equation by r squared, the left-hand side becomes r squared times cosine squared of theta, and the right-hand side, after distributing that factor of r squared to each term, becomes r squared minus r squared times sine squared of theta. And so, well, we're a little bit closer to resembling our integrand function, the square root of r squared minus x squared. To finish making it look exactly like that, well, now we just need to take the square root. Maybe it's not exactly like it yet, but it's going to be closer. And so what happens to the left-hand side once we take the square root of r squared times cosine squared? We just cancel out those powers of 2, and we get r times cosine of theta. And that's going to be equal to the square root of r squared minus r squared times sine squared of theta. And so now we're about ready to make our substitutions. Right, we really want to turn this square root into r squared minus x squared, or think of this as our r squared minus x squared. If this really was our quantity, the square root of r squared minus x squared, then that means r squared times sine squared of theta would have to be our quantity x squared. So that means x squared should be equal to r squared times sine squared of theta. Then doing the same kind of thing we saw earlier, take the square root, and we find our choice for x. X is going to be equal to r times sine of theta. And so now we know how to deal with the function inside of our integral. The square root of r squared minus x squared is going to be dealt with by making a substitution for x. X is going to be replaced with this new variable, theta. It's going to be r times sine of theta. But again, we're going to have to swap out the differential of x in terms of the differential of our new variable theta. And we'd find that relationship between the differentials just by taking the derivative of each side with respect to theta. So we'll skip the multiplying by d theta stuff, but the derivative of x is dx. The derivative of r times sine of theta is going to be r times cosine of theta d theta. Remember, r is a constant here, so we don't have to use anything like the product rule to take this derivative. It's just the derivative of sine times r. That gives us r times cosine of theta. All right, so now we're ready to start rewriting our integral in terms of our new variable theta. We're going to have to keep this constant factor of 4 along for the ride. And now we're going to have to switch out our limits of integration. Remember, we find our limits of integration just by plugging the old limit values into the substituting equation and then solving for our new variable, in this case, theta. And well, it's actually going to be exactly the same as what we saw in our last example. If we set x equal to our upper limit of integration r, then our substituting equation is going to become r is equal to r times sine of theta. We can then divide both sides by r. And once again, we get sine of theta is equal to 1. What's the solution to sine of theta equals 1? It's pi over 2. So for our new variable theta, our upper limit of integration is going to be pi over 2. And to find our lower limit of integration, we set our old lower limit x value of 0 into this equation, divide both sides by r, and once again, we get that equation 0 is equal to sine of theta, and that occurs when theta is equal to 0. All right, so now we need to rewrite the actual functions inside of our integral. The square root of r squared minus x squared, as we saw by our manipulations over here. If x is equal to r times sine of theta, this is going to turn to r squared minus r squared times sine of theta, and the differential of x is going to turn into r times cosine of theta d theta. But remember, the whole point of this trigonometric substitution was to allow us to kind of get rid of or rewrite that square root quantity. And from this manipulated version of our Pythagorean identity, we know the square root of r squared minus r squared times sine squared of theta is the same as r times cosine of theta. So now what does our integrand look like? Well, we have r times cosine of theta times r times cosine of theta. So we end up with r squared times cosine squared of theta. And so going from this line to this line, I've just multiplied those factors of r times cosine of theta together to get r squared times cosine squared of theta inside of the integral. And then I also recognized, well, r or r squared is just a constant. It's a constant factor that I'm going to pull out and combine with that other constant factor of 4 in front of our integral. So now we're really just down to evaluating this integral again, the integral from 0 to pi over 2 of cosine squared of theta. And so just like in our previous example, in order to evaluate this trig integral, we're going to have to use our power reducing formula due to that even power of cosine that is involved. And so we'll remember our power reducing formula was that cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. But I've gone ahead and brought out that factor of 2 in the denominator and absorbed it with our other constant factors in front of our integral. So those constant factors simplify to give us 2r squared. The antiderivative of 1 is theta, and the antiderivative of cosine of 2 theta is sine of 2 theta over 2. Just like before, we have to evaluate this at our upper limit of integration, pi over 2. That gives us pi over 2 as the overall value, and we have to subtract away from that our antiderivative evaluated at our lower limit of integration, which is 0. So that makes everything 0. So what we really end up with is 2r squared times pi over 2, but those factors of 2 cancel out, and what are we left with? Well, pi r squared, and that's our formula for the area of a circle. One of those very early geometric formulas that you learn back when you're a little kid, but now we finally derived it using calculus. Welcome back, everyone. In this video, we're going to look at another example of using trigonometric substitution to help us evaluate an integral. This time we're looking at an indefinite integral. We want to evaluate the indefinite integral of x cubed times the square root of the quantity 1 minus 4x squared. So in our first two examples, we saw examples of what are called sine substitutions. And here I have a general note about those sine substitutions, like when do we know or when should we try to use one of those? Well, if we encounter a quantity like the square root of some constant squared minus our variable squared in our integral, then we might try to use one of these sine substitutions. We're going to try to write things, that is our integrand, in this form if that is showing up. The square root of a squared minus a single x squared If that is the way it is written, then we can set x equal to a times sine of theta. The differential of x will then be a times cosine of theta d theta. And with this choice of x, our Pythagorean identity will help us simplify and rewrite our integral, hopefully in terms of some trig integral, which we can then evaluate. All right, so let's go ahead and see what happens in this example when we try to use this trig substitution. One more note before we jump into this example is we are looking for this quantity, the square root of a squared minus x squared, to help us identify should we use a trig substitution or not. But we want to be a little bit mindful. Just because we see that quantity doesn't mean we need to jump right into a trig substitution, because other methods may actually end up being easier. In this example, this is going to be the way to go, but if we had a similar example where maybe we didn't have an x cubed, but just a single x in front of our square root, then we actually could solve that using a trig substitution, but it would be much, much easier and consume much less time if we just used a normal u substitution instead. So here, a normal u substitution would not work, so we're going to try our trig substitution. All right, so we are just about ready to express our original integral in terms of that starting variable x in terms of our intermediate or new variable theta. But before we do that, we have to identify what a value do we want to use here. And so to help us identify the correct a value, we might need to manipulate or rewrite our integrand function, or at least that square root piece. Right? Notice our kind of general setup here is we have a squared minus x squared. We don't want any coefficients in front of that x squared quantity. Well, here we have that coefficient in front of x squared being 4. We need to rewrite that so that we just don't have that 4 in the way. Well, one way we can get that 4 out of the way without changing the actual value of our expression is by factoring a 4 out of negative 4x squared, but we'll have to also factor it out of everything inside of our square root quantity. So if we factor a 4 out of 1, we'll be left with 1/4. And if we factor a 4 out of negative 4x squared, we'll be left with negative x squared. And so next we can use some properties of square roots to rewrite this in a simpler way, right? If we have a square root of a product, we can write that as the product of the square roots. So this is also the same as the square root of that first factor of 4 times the square root of our second factor, 1/4 minus x squared. And now we are in that kind of general form for our sine substitution. We have a squared minus x squared, and now we can see a squared is equal to 1/4. So our a value is actually going to be 1/2. So this is kind of the general sine substitution form for our particular example. We found our a value is going to be 1/2. So we're going to set x equal to 1/2 times sine of theta, and that'll cause the differential of x to be 1/2 times cosine of theta d theta. Now we are ready to start expressing our original integral in terms of our new variable theta. All right, so we're going to have to swap out every single piece involving x in terms of our new variable theta. So the first one is x cubed. We know a single x is equal to 1/2 times sine of theta. So if we cube both sides of this equation, we'll see how to express x cubed in terms of theta. It's going to be 1/8 sine cubed of theta. All right, so up next is the square root piece. What's going to happen to 1 minus 4x squared if we set x equal to 1/2 times sine of theta? Well, when we square x, we get 1/4 sine squared of theta, and that factor of 1/4 in front of sine squared of theta is going to nicely cancel out that factor of 4. And so we can't forget the differential of x. That's the piece that most people forget when making these substitutions. We know the differential of x is going to give us a factor of 1/2, a factor of cosine of theta, and our differential of theta. So now let's go ahead and simplify our new rewritten integrand before we try to evaluate and find any antiderivatives. So everything here is multiplied together, so we can multiply the 1/8 and the 1/2 and combine those factors to give us 1/16. We have a sine cubed here. Remember, this is the square root of 1 minus sine squared of theta after we simplify it. And by our Pythagorean identity, we know the square root of 1 minus sine squared of theta is going to turn into just a single cosine of theta. So we have 3 factors of sine from this factor out front. Our square root quantity simplifies to just a factor of cosine of theta by our Pythagorean identity, and we can combine that with our other factor of cosine of theta that came from translating the differential of x in terms of the differential of theta, and so that'll give us a total of cosine squared of theta. Alright, so now we have successfully rewritten our original integral that was in terms of x in terms of our new intermediate variable of theta. So now we can start finding antiderivatives, but what's going to be a little bit different about this example that wasn't an issue in our previous examples is if we find the antiderivative at this moment and stop, our antiderivative will be in terms of this new variable theta, but we're going to want to rewrite our antiderivative in terms of our original variable, which was x. So once we get to that point, we'll see exactly what steps need to be taken to achieve that goal. But the next thing we have to do is integrate this function, which is powers of our trig function. And since we have this nice odd power of sine, it's not too bad to do. We're going to have to rewrite it. Maybe I'll pull out that factor of 1/16 in front of the integral while I do this step. Remember, when we have these odd powers, what we usually end up doing is stripping off 2 of them and then using a Pythagorean identity to rewrite all but one of those factors in terms of the other trig function. So here we're going to use the fact that sine squared of theta is the same as 1 minus cosine squared of theta. And now I'm going to multiply all these quantities together except that factor of sine. So I'll have to distribute a cosine squared inside of those parentheses. So 1 times cosine squared gives us cosine squared. Then we're going to have to subtract away from that cosine squared times cosine squared. But that gives us cosine to the 4th. We still have our factor of sine of theta and d theta that we have to deal with. So now where do we go from here? Well, now we have to use a different substitution. Now we have to use a u substitution. So we'll set u equal to cosine of theta. Then du will be negative sine of theta d theta. All right, so now let's just go ahead and go through the steps of our u substitution. So inside of our parentheses, we're going to have a u squared minus u to the 4th. And then sine of theta d theta is negative du. So I'll go ahead and throw that negative factor, that factor of -1 out front with our other factor of 1/16. And then we're going to have sine of theta d theta become du. All right, so can't forget about that factor out front of -1/16, but then we just need the antiderivatives of u squared and u to the 4th, which are very easy to find using our power rule for antiderivatives. That'll give us u cubed over 3 minus u to the 5th over 5. Then plus some constant c, of course. And so we finally found an antiderivative. There's no more integrals involved, but we don't want to leave our final answer like this because our final answer at the moment, well, it's not our final answer, but our answer at the moment is in terms of the second variable, or really third variable, u. Remember, our first variable was x, then through our trig substitution, we went from x to theta, then from a u substitution, we went from theta to u. Well, now we have to go backwards. So first we're going to have to go from u back to theta, then from theta back to x. Well, going from u to theta is very easy, just how we always do for these u substitutions. We just back substitute. Every single factor of u becomes a factor of cosine of theta. So we'll get cosine cubed of theta over 3 minus cosine to the 5th of theta over 5. All right, so remember the substituting equation that got this whole problem started, that let us get this far, was that x was equal to 1/2 of sine of theta. If we had sine of thetas involved in our final answer, well, then it'd be easy to back substitute, but unfortunately we do not. We have cosine of thetas instead. So now what we have to do is figure out how do we use this relationship between sine of theta and x to help us find a similar relationship between cosine of theta and x. There's actually a few ways to do this. One is just using your Pythagorean identities. But another way, the way I prefer, is by using some right triangle trigonometry, right? If we solve our substituting equation for sine of theta in terms of x, just by multiplying both sides by 2, that tells us that sine of theta is equal to 2 times x. Well, we can interpret any of these trig expressions using a right triangle, right? If this is our right triangle and this is our angle of theta, then we can remember that our sine ratio always gives us the ratio of the side length opposite of our angle to the hypotenuse of our right triangle. So now we can just set up a right triangle that'll give us that ratio of opposite over hypotenuse being 2x. We can make the opposite side length of our angle theta 2x and the hypotenuse 1. That way, if we take sine of this angle for this right triangle, we'll get opposite over hypotenuse is 2x. So sine of theta is equal to 2x. And now we can use this right triangle to help us find cosine of theta. Well, here we can just use the Pythagorean theorem. We know this squared plus this squared is going to have to equal the hypotenuse squared. So if we solve that for our adjacent side, we should end up with the square root of 1 minus 4x squared. And you may notice that that square root quantity, that missing triangle side length piece, is showing up in our original integrand. That's not really a coincidence here, and that's a good way to check if you're setting up your triangle correctly. That kind of original expression should be there at some point. All right, and so what this right triangle finally allows us to do is it tells us how to express cosine of theta in terms of that starting variable x. We know that cosine is the adjacent side length divided by the hypotenuse. Well, adjacent divided by hypotenuse here gives us just the square root of 1 minus 4x squared. And so now to finish this problem off and get our final answer, we just need to replace each of these cosine quantities with the square root of 1 minus x squared. And remember, we can also write this as 1 minus 4x squared to the power of 1/2. That'll help us rewrite with all this exponent notation going on. All right, we got this one last step of back substitution to finish this problem off. So we're starting off with that factor of negative 1/16 in front of all these expressions. Then inside of these brackets, we have cosine cubed of theta over 3. We know cosine of theta is the quantity 1 minus 4x squared to the power of 1/2. If we cube that, then we have that exponent of 1/2 cubed. That's just using our exponent rules. We multiply those exponents together. So we can rewrite that piece as 1 minus 4x squared to the power of 3/2. We have to divide that by 3. Can't forget that. And then we have to subtract away from that the quantity over 5 cosine to the 5th. Well, cosine to the 5th is just going to be this expression raised to the power of 5. So that'll give us 1 minus 4x squared to the power of 5/2. And this was an indefinite integral, so we can't forget our constant of integration plus c. But it took quite a bit of work, but we finally have it. This is the antiderivative of our starting function, x cubed times the square root of 1 minus 4x squared. And we won't take the time to do this together, but if you do go through the effort of differentiating our final answer, it should take you back to right where we started, because this is the antiderivative of our original function. One final note about this problem, an observation you want to make and be aware of, is in this problem we saw that we had 3 variables overall and we had to back substitute 2 times. That is often the case with these integrals that involve trig substitution. You'll actually have to make multiple substitutions along the way.